Today we shall discuss Fourier transform or start discussion on Fourier transform. Fourier transformation or transform is a technique which was developed in connection with the solution of differential equations. Furthermore, it is found that this technique is very helpful in evaluating definite integrals, and furthermore it is extensively used in the study of quantum mechanics and as well as the spectral analysis. Actually, if we have a function in position basis, that is, I am writing a function f of x as a function of x, where x is the position coordinate, then what would be the form of the function when we look it into another form, k, wave vector k, which is the, if we consider the dimension of k, it is reciprocal of x. Similarly, if we have a function of time, then it, after Fourier transform, it goes to a omega, where the dimension of omega is inverse of that of time. So to say, the Fourier transform transforms a function from one space into its reciprocal space, into the reciprocal state. The introduction of Fourier transform can be given in many ways, but we shall start from the Parseval theorem for complex Fourier series. So let me recall Parseval theorem. Or equality for which is, if we have a function f of x there which satisfies Dirichlet's condition in AB, then Parseval theorem states that integrated from a to b is equal to delta summation over n from minus infinity to plus infinity Cn modulo square. This is the Parseval theorem applied to the interval a to b. Let me first have a pictorial interpretation of this. The pictorial interpretation of this is, this is x n value, this is n value. I am first writing the right hand side. Say the and y axis, along y axis we plot modulus Cn square. So this is the point, and now so on so forth. So that means this much is C0 square, this is C1 square, C2 square, C3 square, and come similarly on the negative side. So these are the values of the function. So this is the sum, this sum extends on either sides, and this is the interpretation of this sum. If we go to the right hand side, it is the area under the curve This is the area under the curve. So the red line is actually represents the integral on the left hand side, and the broken and the hexagons represents the sum on the right hand side. If we consider this, the right hand side could also be given an interpretation in terms of integrals if we let a and b tends to infinity. So let me once again say the left hand side represents the area under the curve between a and b, while the right hand side is the sum of the Cn modulus square for different n's. Instead of being this arbitrary interval, if we choose that a is equal to minus L and b is equal to plus L, so that delta is equal to 2L, the integration becomes minus L to plus L modulus fx square dx this is now we know that in Fourier transform, if we want to calculate Cn, a factor appears. The factor is basically Cn is 1 upon delta summation from integration from this to this I this quantity, look at this quantity. It is in the numerator, if we consider this is 2n pi, in the numerator all the quantities are dimensionless, and in the denominator the quantity that we have used has the dimension of x. So if we call k, this quantity is k, then the dimension of k is inverse of L. If L happens to be space coordinate, then it is 1 by x square, and if it is bt, then it is 1 by t. That is what we are going from one space to another space. Now you note that this n value changes by 1. That is, if we consider if we take a differential of this is delta k is equal to 2 pi upon delta n, or delta n, the change in n is 1 and is equal to delta upon 2 pi times delta k. So we can multiply each term by delta n, so that the Fourier, now the Parseval's theorem becomes from minus L to plus L. On the right hand side we will have delta times Cn modulus square, sum over n from infinity plus minus infinity to plus infinity is implied. Then we multiply each term by 1, that is now use the expression for delta n as this. So this becomes where we have defined AL of K as delta upon root 2 pi Cn. The argument K has been introduced because C has K dependence. Recall the definition of C. So once we integrate this, the resulting quantity will have K dependence, and furthermore it depends on the value L. So that's it. That is the reason for using this notation. Now what happens when L tends to infinity? So we define a quantity A of K as limit L tends to infinity. Oh, sorry, I have forgotten to write the 1 by delta quantity, so that this resultant quantity will be 1 upon root 2 pi 1 upon root 2 pi minus L to plus L f of x e to the power minus I k x dx. So when limit tends to L tends to infinity, AL of K, which is simply 1 upon root 2 pi integration from minus infinity to plus infinity f of x e to the power minus I k x dx. Now in such case, recall the expression for K. K is equal to 2n pi delta. This is, in our case, is n pi by L, as delta is equal to 2L, and delta K is equal to pi L delta n. As L tends to infinity, delta K tends to 0, in which case we can replace this by an integral over K. So we write, let me consider that this case is equal to when L tends to infinity. This is an integral over a k square dk integrated from minus infinity to plus infinity. So this is the new form of Possible's theorem. This quantity is equal to this, where we have defined AK in this fashion. A similar expression can be obtained for f of x also. So let me first write the summary and then is equal to this quantity this is the new possible theorem, with A of k is defined as what happens to f of x representation in this case? So let me come to the expression for f of x. In complex Fourier series, we express f of x as sum over n from minus infinity to plus infinity. That is, we write it as you recall the definition of an, al of k. It was delta upon root 2 pi and it is Cn. So if we replace Cn by Al, this becomes delta upon 2 pi, root 2 pi by delta and we introduce delta n here. Since delta n is 1, since this is 1, and you know that delta n is equal to what? Is equal to n is equal to L by pi k, so delta n is equal to L pi by delta k. So this becomes root 2 pi by delta L of k ikx, and now we replace L. So if we write it in terms of delta, it is delta upon 2 pi delta k. So multiplied by delta upon 2 pi delta k. On simplification, the numerical factor becomes 1 upon 2 pi. This is this adjustment. Then we will have Al of k e to the power I kx delta k sum over n, which in the limit L tends to infinity, this becomes very small, and we can convert this series sum by an integral. This will be a of k in the limit L tends to infinity e to the power I kx dx. So, if we consider a Fourier transform within symmetric interval plus minus L, and then we let the L tends to infinity, then we can write the function as this, where AK is governed by this. So, the summary is this. Let me summarize the fact. So, if we allow the very large number n, this n tends to plus infinity on the right and minus infinity to the left, then if we look the entire range of n at a time, then although delta n is 1, but it will appear as very small, and we can consider these hexagons as a continuous curve, and we can evaluate the area under the curve. So we find that we conclude that if we define a function f of x within symmetric limit, then if L tends to infinity and the system is defined within plus minus L, then we can write f of x is equal to 1 upon root 2 pi integration a of k e to the power I kx dk from minus infinity to plus infinity, where a of k is governed by 1 upon root 2 pi minus infinity to plus infinity f of x e to the power minus I kx dx. These two if we call this as the Fourier transform of f, then f is the Fourier transform of k. So these two are the Fourier transform pair. If generally we call a of k f of x, then f of x, and one generally uses the notation like this. Fourier transform means f and the inverse Fourier transform f of x is the and it is generally written as f inverse a of k. There is no hard and fast rule which is the forward transformation and which is the inverse transformation. If we call it is the forward transformation, then it is inverse transformation. Someone as well call it as the forward transformation, then it will be the inverse transformation. So we get the result where ak is governed by this relation and f of x is governed by this relation. We can also define Fourier transform or other transform in a general perspective called the integral transformation. One point, Fourier transform can all. Here we have a derived Fourier transform as a limiting case of complex Fourier series with L tends to infinity. We have started the Percival's theorem as our starting point. We can as well define Fourier transform from the trigonometric Fourier series and letting L tends to infinity. There is another way, as I was talking about, the integral transform. In the solution of differential equations, such integral transforms have been used. The integral transform is generally defined as this. We consider a function f, then we integrate it from some limit. K2, this is an integral, this is a relation, and inverse relation is written as this quantity is called kernel of transformation. This is called kernel of transformation. Now, as in the case of Fourier transform, the kernel is, for forward transformation, k of xk is e to the power I kx and 1 by root 2 pi, and the inverse kernel is this is, and now x, this is k1 and x1 are infinity, x1 k1 tends to minus infinity, and x2 k2 tends to plus infinity. This is the definition of Fourier transform in terms of integral transformation and the kernel of transformation. There are other transformations, as for example Laplace transformation, in which case x1 k1 is equal to 0, x2 k2 tends to infinity, and the kernel k of xk is equal to the inverse kernel k of xk is equal to e to the power minus kx. So this defines the Laplace transform. There are other transformations like Bessel transformation, Hankel transformation, Hermite transformation, Milan transformation, and so on and so forth. Each of the transformation has specific use in the solution of differential equation. Now we come to the Fourier transform again and see what the form becomes when we consider even and odd functions.